Hello. Today I want to go over problem 2018 J5, choose your own path. Before watching this video, I recommend you familiarize yourself with the problem. But the gist is you're doing a choose your own adventure book, and we need to figure out two things. We need to figure out if every page in the book can be reached, because there might be some where no page jumps to them. So we need to figure that out. And we also need to figure out the shortest path to an end point. Because, in Choose Your Own Adventure books, like there's multiple endings that don't go anywhere from there. And so we got to find the shortest path to unending. So the first line of our input gives us the number of pages in the book, and the pages are numbered 1 through n. So I'm going to make things a touch bigger than I need to, just so I can ignore index 0 and have just indexes 1 through n rather than 0 through n minus 1, because that's more annoying. So our first input will be the number of pages. I've done that right here. I've got a scanner, and then I grab the number of pages, and then the next output is just kind of like here. You've got n lines after that. Notice we got 3 pages and then 3 lines after that. First thing in every line will be the number of different pages you can jump to. So this is page 1, and we can jump to 2 pages from page 1. We could jump to page 2 or page 3. And then page 2, we can't jump anywhere. So that's an ending. Anything with just a 0 is an ending page, and 3 is an ending. Keep in mind our shortest path is 2, because it does include page 1 and page 2, or page 1 and page 3 are our shortest paths. And so that's what we got to do. So this is like perfect question for learning breadth first search. This is just basically breadth first search, because one, we got to check that all pages are reachable from page 1. So we're going to need to do a search of some form, either depth first search or breadth first search, to pull that off. Just see which pages we can visit from 1. And we also got to find shortest path, so that puts breadth first search in the lead for what method to use. So let's do it. To do breadth first search, we're going to need a queue. So I'll make a queue of integers representing the page we're going to jump to next. I'll be boring and call it a queue. And that's just a new linked list. So we're going to need that to implement our breadth first search. I'm going to use a hash set to see which pages I've visited. I'll call it visited. A better option might be like this will make sure I don't end up going in loops. Say page 1 links to page 2 and page 2 links to page 1. So we don't want to go to previously visited pages, because then our code will just never finish. So we do need something to mark the places we visited. So a hash set is great for that. It doesn't allow duplicates. And it's also going to be really handy because at the end of it all, if I want to figure out if all pages are visitable, I can just check the size of my hash set. And if that matches my num pages, then all pages are reachable from page 1. Because hash sets are sets in that they don't allow duplicates. So you can add 1 53 different times, but it's still only got 1 in the set once. This is going to be handy to both keep track of places we visited so we don't end up forming loops and loop going forever, and also to see if all pages are visitable. Faster way would probably be a Boolean array for all the pages, where you just mark it to true if you've been there, and then keep a counter. So every time you do switch a page to true, you increase the count by 1. So that might be a slightly faster way, but I want to show you the hash set, so that's what I'm going to do. So that will just keep track of our visited places. And then one of the most important things is we've got to come up with some sort of representation of our graph. This is a graph. We need to represent how each page links to other pages. And I almost always use an adjacency list, which sounds worse than it is, but it's really just for every page, we're going to have an array list that holds all the other pages we can jump to from that page. So I'm going to do an array of array lists. So this is what that looks like. We're going to have an array list of integers, but an array of those. And I'm going to call this, I don't know, adjacency, or no, maybe I'll just call it kind of neighbors. Next pages. Sure, next pages. And that's going to be a new array list, and I'm going to want an entry for every page. So, and I also want to start at index 1 and go to index num pages. So I'm going to make this num pages plus 1 and just ignore index 0, because then I don't have to shift indexes and have things be annoying that way. I can handle the extra couple bytes in memory. All right, now we just gotta fill up our adjacency list. So that's all done. So we're just gonna do that for every page. So int I equals 1. I is less than or equal to the num pages. I plus plus. And then I'm going to make a new adjacency list, or maybe I'll get int num neighbors, if I can spell it, neighbors equals input dot next int. So right here, for every page, I'm grabbing this guy, the number of neighbors it has, the number of pages I can jump to from there. So that grabbed that, and then for int j equals 0, j is less than num neighbors, j plus plus, I'm gonna grab all the neighbors and put them in array lists. So I'm gonna make an array list of integers and call that the current list. And that's just a new array list, blah, blah. And so I will just update my current list. I will add the next int I can grab. And that'll just grab the correct number, given that it'll only happen num neighbors times. And then just in my array list, or array of array lists, in my next pages for entry I, which is the current page, I'm gonna put in the current list. And there we go. So that should build out our array list. Just for every page, we grab the number of pages it can jump to, and then we make an array list to hold those next pages for the current page. And then we grab those numbers and add them to this array list, which will be the list of neighbors for the current page. And then we set the entry for next pages for the current page to that list we just made of all the pages you can jump to from there. So that builds up our adjacency list. So now we just got to do breadth first search. So I'm going to do something like while the queue is empty. I guess I got to add something to the queue. So I'm going to need an int to hold the distance from the beginning. I'm going to start it at 1 because the current page, even if it ends at, like if the current, like page 1 has 0 neighbors, that would still be a distance of 1. I should also have a min distance. I'm going to start that at like num pages. I'm pretty sure it's not going to be that, but I'll throw that in there. And then I'm probably just going to have a Boolean just to say if I found min distance. Should be slightly more efficient. I could probably just update it every time, but this will be slightly faster. What else do I need? I will need distance on pages. I gotta add the first guy to the queue. So I'm gonna, to my queue, I will add, what do I call my queue? Queue. I will add page 1, and then I'm also going to add a sentinel value. Now this is a number that can never show up naturally. That is just a signal. So every time I run into that signal, I'm going to do something different than the normal. So then we got our breadth first search. I'll do a little while loop. I'm going to say, well, q dot size is, or maybe not q dot is empty. You could also do size is greater than 0. So while the queue isn't empty, I'm going to grab the first thing in the queue. So I'm going to say and current q dot poll, and then I'm going to have if it's the sentinel value. So if current is -1, I'm going to do one thing, and if it's anything else, I'm going to do something else. So if it's a -1, I'm going to increase distance by 1 because the first page is the only page possible at a distance 1 away from it. Then I'll hit the sentinel value. I'm going to up it to 2. By the time I've processed 1, I will have added all the neighbors after that -1, all the neighbors I can get to from 1. So those are all the ones distance 2 away. And so I will also throw, so I'm going to say, hey, if the, so right here I need a little if statement to protect at the end. I don't want to just keep making -1s forever. So if I have nothing except a -1, so I'm going to say, hey, if the queue is empty now, so if queue or dot is empty, or if it's not empty, so I've used up the current -1. If it's not empty, I'll add another -1. So I'll do q dot add. This is just kind of like, you know how I said that as soon as I hit this -1, I would have hit all the neighbors of 1, all the pages I can get to from 1. So that would be all the ones of distance 2 away. So at the end of all the ones distance 2 away, I want to throw in a -1. So I know I've hit, once I hit it, I've hit all the ones distance 2 away. And then I want to add my distance to 3 and also throw in a -1 at that point, because that will be after all the ones distance 3 away. Think it through a bit, see if you can have that make more sense to you. But anyway, this deals with all the sentinel values and our distances. And aside from that, we just need to jump to all the non-visited neighbors of the current guy. So we'll go to our adjacency list, and we're going to say, hey, for every page we can jump to, notice I'm using a for each loop. In the current guy's adjacency list, and that is current. So page will be equal to all the different pages I can jump to from the current page. And for all of them, I want to say, hey, if they are not in visited, not visited contains the page. So if I've never seen the page before, I will add it. Next, I'm going to check to see if this is the one page, the closest ending to the start. So I'm going to say, hey, well, first I'll update the distance. So I'll say, hey, I guess I don't need to know that. So I'm going to say, hey, if the what do I call it? Next neighbors, next pages. If next pages for the current fellow, which is page, if its size equals 0, then actually I should also check if I have not found my min distance. So if I've not found my min distance and it's an ending page, then it must be the closest ending page if I haven't found a min distance so far. Then I'm going to say min distance equals distance, the current distance from the beginning. And that should do her. Oh, and I should also update my found min distance now should equal true, because I have found the closest distance. So first thing I want to check if I've visited the page before. If I haven't visited the page, I'm going to check if it's the first end page, and if so, I will make that my min distance and say I've found it. I also want to add it to the queue, so I want to jump to all of its neighbors. Oops, maybe I will make this a separate if statement. So for found min distance, I want to do everything. Oh, crud. Oh, no, never mind. Never mind. Sorry. Making an error here. Okay, so this is all the junk I want to do if it is the next new page, but if it's not visited, I always want to add it to the queue so I can add all its neighbors. And then I think this might be everything I need. I deal with kind of how to end it. Grab the current one. If it's sentinel value, I increase my distance and update the sentinel value. Otherwise, it's just a normal page. And so for all of its neighbor pages, I check if it's visited. Actually, since I don't look at the first one, I should put this right at the beginning. Apologies. I am getting confused. Okay. So I'll throw this, sorry, right after the, if it's a -1. Okay, and then at the very end, I just need to print the y or no. So I'll do it with an if statement because not all of you know ternaries. So if visited dot size is equal to num pages, I'm going to say that they're all reachable. Else I'm going to print out an n. And I will also print out the shortest path, which I called min distance. Now, I'm just going to check that this works quick. All right, I had a couple little errors. Here's what I needed to do. When I added 1, I also needed to add it to my visited queue. I needed to, every time I added a new page, I needed to also add that to my visited, sorry, not visited queue, but visited hash set, keeping track of all the pages I've been to. And I also had this if statement right here, like beside the -1 thing, so it's picking up the -1, so it needs to be inside the else, because I do not want this triggering if current is equal to -1. So, quick explanation of everything. We grab all the data, we put it into an adjacency list representation. So every page number is associated with an array list that is equal to all its neighbors, all the pages you can jump to from that page. And then we add 1 to our queue. We add -1, which is our sentinel value, which means we do something a little different at that point. That means every time we hit that, we've hit kind of the end of all the ones a distance 1 away from the queue, or all the ones distance 2 away from the queue, or all the ones distance 3 away from the queue, and it's time to update our distance from the start using that. And then I've got to keep updating my hash set because that will tell me if I've visited every point. I've got to add 1 because that won't naturally happen here. Aside from that, I grab the first, well, the queue is not empty. I grab the first thing in the queue. If that thing is a -1, I do my -1 thing, adjust my distance, throw a new thing in the queue if the queue is not now empty, because that would signal that we're done. Otherwise, if it's not a -1, I check to see if it is the new shortest distance thing, or the shortest distance thing I've seen so far. And if it is the first ending page that I ever run into, if I've not found a min distance before and it's an ending page, then it must be the minimum distance ending page, because breadth first search, the first ending page you see will be the closest to the start. And so we set that to be the min distance, and I'm just going to throw this in there just so I don't keep checking it again and again and again. And then for any other page that's not a min distance one, for all the pages I can jump to from there, if I haven't visited it before, I add it to the queue. I also add it to visited, so I don't try to add it multiple times. And then at the very end, if I've managed to, if the size of my visited set equals the total number of pages, I must have been able to reach all the pages from the start. If it's not equal, I must not have. So I'm returning no, and I print the min distance. Hopefully this is helpful. Thanks for listening.